The title of my talk refers to Jerome Klepka Jerome's classic novel, 3 Men in a Boat, to say nothing of the dog. It is much beloved by many people throughout the world, including by Nati and myself. Now, Nati read it in Hebrew, and the Hebrew version differs a little from the English version. And so, Nati, here is an English copy of 3 Men in a Boat, to say nothing of the dog. For those of you who don't know it, well, if you can get nothing better out of this talk, get a good book out of it at least. Prologue. There were 4 of us: Nati, Jeffrey Samuel Harvey, and myself, and Mel DeChena. We were sitting in my office, Skyping and talking about how confused we were. Confused from a conceptual point of view, I mean, of course. With me, it was my talk that was out of order. I knew it was my talk that was out of order because I had just been reading a blog in which were detailed the various mistakes by which a man could tell when his talk was out of order. I made them all. Nati said, "You know, you're on the wrong track altogether. You must not think of the results you can do with, but only of the results you can't do without." Nati comes out really quite sensible at times. You'd be surprised. I call that downright wisdom. Chapter 1. An orbifold by T-duality, a one-loop anomaly and a puzzle. Nati is sarcastic. An old condition revisited. So we begin with the question, can you orbifold by T-duality? This is a question that came up in some recent work I've been doing with Jeff on Mathieu Moonshine, which I'll tell you all about some other time. And we were not the first to ask this question. It's been known for some time that it would be a nice way to make monodrafolds and T-folds. And the simplest example is just to consider a periodic scalar at the self-dual radius. So T-duality acts by taking x left to x left and x right to minus x right. Now, this model is anomalous. It has a one-loop modular anomaly in the G-twisted sector. If you calculate the energies on the left, you get a half p left squared plus integer-moded oscillators, and you can show that that's equal to an integer over 4. But a Z2 twisted scalar has a ground state energy of 1/16 plus half integer moded oscillators, so these two can never match, so this model is inconsistent. But if we take 4 copies of the Gaussian model, then we have a 4/16 as a fourth, and now we can match the energies, and so the model is consistent. But even with this consistent model, something peculiar is going on. You see, if you look at the one-loop partition function with twisted boundary conditions, untwisted in the space and twisted by T-duality in the time direction, then you can make a tau to minus 1 over tau transformation to the twisted sector partition function. And now you can make a tau to tau plus 1 transformation to twist in the time direction. If you do it twice, and you explicitly calculate these, you find that this partition function is not equal to this one, not even up to a phase. So that's funny. T-duality is supposed to be an involution. R goes to 1 over R. You do it twice, it's the same thing, right? Well, if you just keep going, you find that after 4 tau to tau plus 1 transformations, you do come back to the original partition function. And so in the twisted sector, G is actually order 4. Now, Jeff and I thought, well, you know, twisted sectors, they're funny things. So still, G has to be order 2 in the untwisted sector, and making that assumption, we calculated the partition function for the whole theory, and we found negative half-integer degeneracies. And we were quite confused about that for a while until we talked to Nati, who said, why don't you think what you're doing? You go about things in such a slapdash style. You'd get a scaffolding pole entangled. You would. And indeed, at the self-dual point, the Gaussian model has an SU2 left times SU2 right symmetry. And you see, the currents form a triplet of SO3 right, and T-duality does this. So T-duality is a 180-degree rotation in SO3 right, and that lifts to an order 4 element in SU2 right. So it's order 4 even in the untwisted sector. Once you've got that straight, you can go and calculate the partition function. Gives a perfectly sensible partition function. As far as we know, this theory is completely sensible and can be used in a string compactification. But this is all related to asymmetric orbifolds. These are examples of asymmetric orbifolds. Now, almost 30 years ago, Narain, Sarmati, and Vafa gave general consistency conditions for asymmetric orbifolds, generalizing those for symmetric orbifolds that had been written out in the foundational work of Dixon, Harvey, Vafa, and Witten. But one condition was a little mysterious. In the case of an involution, P.gp, they said P.gp has to be 0 mod 2 for all Narain vectors P. But this is violated by that T-duality orbifold of 4 copies of the Gaussian model. So what Jeff and Nati and I think is that actually this is not a true consistency condition. It means that the actual group that acts on the conformal field theory is really Z4, not Z2. And there's much more to say about this, but we must push on to chapter 2. Philosophy, origins and affine space, Hilbert bundles, Berry's connection, a simple man, band structure, a 3D quantum Hall effect. So I begin with a philosophical premise. If a physical result is not mathematically natural, there may well be an interesting, important underlying physical issue. And I'll illustrate this with continuous families of quantum systems, namely quantum systems parametrized by a space X of control parameters. In this context, one naturally encounters Berry connections, and that's been an enormously successful idea. But what I'd like to talk about here is a little subtlety. If you're given a continuous family of Hamiltonians with a gap in the spectrum, in general, there's not one Berry connection, but rather a family of Berry connections. And this can have physical consequences that I'll illustrate using examples from topological band structure. But the general remark should have broader applications. Now, the slogan that goes with this is that the origin of the problem is the problem of the origin. And to explain what I mean by that, let's review what is affine space. An affine space is like a vector space, but there's no natural choice of origin. So the official definition is that an affine space is a space with a transitive and free action of a vector space. Now, we all use affine space all the time when we pretend that the Earth is flat and we use a map. So this is a little piece of affine two-dimensional space. And I ask you, where is the origin? Now, many of you will say it's in Princeton. But some of you will say, no, it's in Boston. Others will say it's in Santa Barbara, and yet others will say it's at Stanford. But there's no natural choice of origin. Now, it's true that the difference between Santa Barbara and Princeton is a vector in a vector space. Put differently, if we have a vector in a vector space, we can translate from Princeton to Santa Barbara. Now, that's a very simple example, but bear in mind that the space of connections on a vector bundle is also an affine space, and we'll come back to that. Now, in Berry theory, we start with Hilbert bundles, namely a space H with a projection pi to control parameters, and then over any particular control parameter, little x, we have a Hilbert space. So the picture is you have this total space, and the fiber over a particular control parameter, little x, is a Hilbert space, H sub little x. Now, the space of sections is denoted by gamma, and a section, capital psi, is a continuous assignment of a vector, little psi of x and h of x, continuously associated to the control parameter, little x. So in our picture here, we assign a vector in the Hilbert space for every little x. Now, a connection on a vector bundle is just a map from the space of sections of the vector bundle to the one forms valued in the vector bundle, which is a first-order differential operator. So it satisfies this Leibniz rule. And as I just mentioned, the space of connections on a vector bundle is an affine space based on the vector space of one forms with values in the linear transformations of V. So the difference of two connections is this one form alpha, and alpha mu at any particular x is a linear operator from the fiber to the fiber. Now, unless the bundle is trivial, namely it's literally a Cartesian product of x times a fixed vector space, then there is no natural origin in the space of all connections. Okay, now, the other ingredient we need for Berry connections are projected bundles. So supposing we have a continuous family of projection operators, P of x, then we can define the projected bundle whose sections are eigenvectors of P of x of eigenvalue 1. And a very popular example is to take the trivial bundle, S2 times a qubit, with the projection on the first vector, and take the projector to be the projection onto the spins in the x-hat direction, and then the projected bundle is the Hopf line bundle with non-trivial first Chern class. Now we're ready for the Berry connection. So supposing we have a continuous family of Hamiltonians, H sub x, on Hilbert spaces, curly H sub x, and suppose there's a gap in the common spectrum of these Hamiltonians. Then we have a continuous family of projection operators. We project onto the linear span of the energy eigenstates with energies below the gap. Then we can form the projected connection, and here's the formula for it. So iota simply takes a section of V and interprets it as a section of H. The connection on the Hilbert bundle differentiates it. In general, that derivative takes you out of V, and so you must project back into V. And I'll denote this nabla B, where the B is for Berry, but it could also be for Barry, because it was Barry Simon who actually first interpreted correctly Berry's mysterious geometric phase. Now, what's not in the literature on Berry connections, as far as I can tell, is the importance of the fact that you need to choose a connection, nabla H, on the Hilbert bundle. You see, it's commonly assumed that H has been trivialized, namely, it's literally a direct product of x times a fixed Hilbert space. And indeed, in that case, there's a natural choice of connection on this Hilbert bundle, the trivial connection. Namely, if we have a continuous family of vectors in a fixed Hilbert space, we can take the derivative and multiply by one form, and that's the origin in the space of connections. And when you see formulas like this in the physics literature, that's what's being assumed. Now, there's a general theorem that Hilbert bundles are trivializable. But in general, there's no natural trivialization of H. Okay, now at this point, I can feel Nati is getting impatient. I'm a simple man. When many of us know this phrase, I'm a simple man. When Nati says this, it means one of two things. It means either that he's about to make an astute and penetrating observation or question, usually making you realize how stupid you've been, or he's getting fed up with this mathematical formalism and he wants an example. Okay, so time for an example. My examples are going to be from topological band structure. And so let's review, albeit very mathematically, a little bit of band structure theory. So I'm going to construct a Hilbert bundle over the Brillouin torus. So supposing we have a crystal in affine n-dimensional space, so it's invariant under a lattice L of translations, and then the Brillouin torus is the set of unitary irreducible representations of L. Now, it's usually presented in terms of the reciprocal lattice. L dual is the dual lattice to L. It sits in the dual momentum space. And the Brillouin torus is the quotient of momentum space by the reciprocal lattice. And indeed, if we have a point k bar in the Brillouin torus, then we have this one-dimensional representation. R is a vector in L, and we take this phase where this k is any lift of k bar. Now, the block states define a Hilbert bundle over the Brillouin torus. The block states are just the quasi-periodic wave functions transforming in this representation where psi k is suitably normalizable. Here you see an example of a Hilbert bundle which is manifestly not a direct product. The very definition of hk bar makes use of k bar. It's not written as a Cartesian product. Okay, now, by the general theorem, there are trivializations. You can choose sets of block functions so that for fixed n, it's smooth in k bar. For fixed k bar, it forms a basis for the Hilbert space. But there's no natural choice of these. There's no natural trivialization of h, so there's no zero in the space of connections, so there's no such thing as the Berry connection in band structure. Now, there is a natural family of connections on H, and I'll denote them by nabla H x naught, and they depend on a choice of origin x naught modulo L. And the difference of two such connections is a one-form alpha, which is a very simple one-form, dk.x naught minus x naught prime times the unit operator on the Hilbert bundle. So now let's apply this to insulators. So in an insulator, we have a Fermi energy inside a gap, and the ground state is at zero temperature, has all the states in the bands below the Fermi energy are filled. So we can define the bundle of filled bands by the projection operator onto the eigenstates below E Fermi. And the Berry connection, or the family of Berry connections, is the projected connection that depends on x naught, and alpha is again given by this formula. Now, you might be thinking, well, this is pretty trivial. I mean, alpha is not a big deal. Indeed, if you calculate the curvature of this connection, it's independent of the choice of x naught. So all the Chern numbers are unchanged, the curvature is unchanged. But you all know that there's gauge invariant information in a connection which is not captured by the curvature. And very beautifully, that gauge invariant information actually shows up in the condensed matter literature. So one place it shows up is in a formula for the contribution of electrons to the electric polarization, and I'm not going to explain this complicated formula, but notice that it depends on the holonomy of the Berry connection around a closed loop in the Brillouin torus, and that depends on x naught. Now, a little less trivially is the magnetoelectric polarizability. That's a term in the low energy effective action for the Maxwell field in the presence of an insulator. And famously, the trace of this tensor is an Axion angle, which is equal to the integral over the Brillouin torus of the Chern-Simons form of the Berry connection. But I just told you that there isn't one Berry connection. There's a whole family of Berry connections. So we should ask, what's the dependence of the Axion angle on x naught? You see, the Chern-Simons form shifts. If I shift the connection by a one-form alpha, the difference of this Chern-Simons form and that one is given by this standard expression. So if you work out what this is in the example that we're talking about, you find the following. You can interpret the integral of the first Chern class of the bundle of filled bands over the Brillouin torus as an element of the reciprocal lattice. So just think of this vector C as a reciprocal lattice vector, and think of it as coming from the first Chern class of the bundle of filled bands. Then it's a straightforward exercise to see that the dependence of the Axion angle on x naught is just given by this formula here. So the Axion angle is ambiguous. It depends on x naught. Now, I was pretty confused about this for a while until I talked to Edward. And Edward told me to just interpret this as saying that that means that theta of x is an affine linear function of x. So take it to be that and integrate by parts. Edward's advice is always good, so let's take it. And this is the effective action that you get. Now, that's a pretty interesting effective action. It means that there's a quantum Hall effect in the bulk of this so-called insulator in all the planes which are orthogonal to this reciprocal lattice vector C. And I was very pleased by this. We started with this fancy mathematical philosophy, and we ended up with an interesting physical result. But then after giving a talk about it a few weeks ago, I learned that actually the basic physics here had been discovered by Bert Halpern 30 years ago. So Bert Halpern wrote a paper about a three-dimensional quantum Hall effect, and this is the formula he wrote, where C is a reciprocal lattice vector. Of course, he took a completely different point of view in deriving this formula. Still, I think the low-energy topological action is a very good point of view. For example, it shows you that dislocations support chiral modes and give physical realizations of surface defects. For example, here is what's called a screw defect. And to an observer far away from this axis here, it looks like you're in an ordinary crystal. Because as you go around, as the planes go around this axis, the helical shift is by a vector d in the lattice called a Berger's vector. Okay, now by standard anomaly inflow type arguments, that means that there are C1.d chiral bosons on this surface defect. Again, I was scooped by the condensed matter physicists, so Vishwanath et al. And Chi et al. Have this result, and others, and indeed this figure is actually from Chi's paper. Nevertheless, I think with this action one can do more in this example, and I'm quite sure that the general remark about families of Berry connections has other physical applications. But it's time to push on to chapter 3. Quantum systems, continuous families, all in the family, noncommutative geometry, Hilbert bundles, a Born rule at last, quantum information theory, hexagons, and pentagons. So by a quantum system, I mean we have a set of physical states, S, and a set of physical observables, O, and a Born rule, a map from states times observables to P probability measures on the real line. That just means if you have a measurable set M, you get a real number between 0 and 1, satisfying some well-known axioms. So if we take the Born rule for a state S and an observable O, and we take M just to be the closed interval from R1 to R2 and evaluate this, we get a real number between 0 and 1, and this is the probability that a measurement of the observable O in the state S has its value between R1 and R2. Now, how is this realized in the standard Dirac-von Neumann axioms? S is the set of density matrices, the positive trace class operators on Hilbert space of trace 1. O is the set of self-adjoint operators T on Hilbert space. And to formulate the Born rule, you need the spectral theorem, which says there's a one-to-one correspondence of self-adjoint operators T and projection-valued measures. What that means is that for every measurable set M, you get a projection operator P of M that depends on T and satisfies some standard axioms. For example, if T has a discrete spectrum, you can write it as a sum over its eigenvalues of lambda times the projection operator onto the lambda eigenspace. And then if we take PT of this closed interval from R1 to R2, we simply get the sum of the orthogonal projection operators for lambda between R1 and R2. So what does the Born rule look like for state rho and an observable T? If we evaluate it on a measurable set M, it's the trace of rho times the projection-valued measure of M. And this is just the formula that you've all learned in your undergraduate quantum mechanics textbooks, I promise. Now, how does this generalize to continuous families of quantum systems? So now we're back in the situation of chapter 2. We have a Hilbert bundle over a space X of control parameters. And for each X, we get a probability measure P sub X, because rho sub X and T sub X and H sub X, they all vary continuously. So really, we should think of the Born rule as a map from states times observables times X to probability measures. So Born rule of rho, T, and X is this P sub X. Now, at this point, we should pause and reflect on what kinds of families X we think are admissible. My friends, there are all kinds of families. For example, there's the bunker family. Now, Many of you will have no problem recognizing the bunkers. But for those of you who don't, the most popular TV show in the 1970s was a sitcom called All in the Family. And it helped many Americans come to terms with the great lurch towards social justice that had taken place in the 1960s. And this show broke all kinds of taboos. In particular, it broadened the notion of what kind of families are deemed socially acceptable. So in that spirit, let's replace the family X of control parameters by a non-commutative space. Now, many of you will be wondering, why do that? And the honest answer is curiosity. And indeed, formulating the Born rule proves to be an interesting challenge. Now, a more respectable answer is that with an irrational magnetic flux, the Brillouin torus is replaced by a non-commutative manifold. It's also true that non-commutative moduli of vacua of supersymmetric field theories have been coming up recently, and for example, Ciccati, Gaiotto, and Vafa were suggesting that we should formulate non-commutative TT star geometry. It's also true that boundaries of Noreen moduli spaces of toroidal heterotic string compactifications are non-commutative, a remark incidentally closely related to the most cited paper of Zyberg and Witten. And finally, who knows how space and time break down in the early universe? But one popular idea is that we should use some more algebraic language, possibly using non-commutative geometry. So for all these reasons, there are potential applications of what I'll say, but the honest answer is curiosity. Now, to talk about non-commutative manifolds, you use the language of C-star algebras. So a C-star algebra is a normed algebra, A, that's a Gothic A, over the complex numbers with an involution. So A goes to A star, and AB star is B star A star, and some other axioms we don't have time for. Now, there are two examples I want you to keep in mind through the rest of the talk. And example one is the algebra of complex valued continuous functions on a topological space X. And example two is just n by n matrices over the complex numbers. Now, for any C-star algebra, we'll say an element is self-adjoint if A star is A, and positive if A is B star B. The relation of C-star algebras to non-commutative geometry is best explained by going through Gelfand's theorem, which says that the topology of a Hausdorff space X is completely captured by the C-star algebra of functions C of X. Okay, the basic idea here is that points are one-dimensional representations. You see, if you have a point x naught, you have the evaluation representation. It takes a function f to its value at x naught. Now, you can go the other way around. If you're given any commutative C-star algebra, you can consider its set of one-dimensional representations, its irreducible representations, and you could put a topology on that space. Well, if it's a topological space, you can talk about the continuous functions on that topological space. And that's another commutative C-star algebra. And guess what? It's isomorphic to the original C-star algebra A. That's Gelfand's theorem. So in this way, we can translate statements about topology and geometry of X into algebraic statements about C of X. And so the idea of non-commutative geometry is we replace C of X by a non-commutative C-star algebra, A. And we interpret A as the algebra, notionally, the algebra of functions on this non-commutative space, even if the algebra A has no interesting one-dimensional representations. That is, even if there are no points. And that leads to the old joke that non-commutative geometry is pointless geometry. So a good example here is the non-commutative torus. It's generated by a lot of unitary operators that satisfy this exchange relation. And if phi ij is rational, then this is Morita equivalent to the algebra of functions on a torus. And if it's irrational, it's not the algebra of functions on any commutative space. It's the non-commutative torus. So we'd like to define a family of quantum systems which are parametrized by a non-commutative manifold whose algebra of functions is a general C-star algebra A. And that raises a lot of questions. What are the observables? What are the states? And what is the Born rule? So before we deal with these questions, let's ask another question. What replaces the Hilbert bundle? Because in this case, there's an off-the-shelf mathematical definition. It's well known in mathematics that a non-commutative Hilbert bundle is something called a Hilbert C-star module over an algebra A. So a Hilbert module is a complex vector space E with a right action of A and a, quote, inner product valued in A. So if psi1 and psi2 are vectors in the Hilbert module, and we look at the overlap, or exists a sesquilinear form on E, psi1, psi2, which is valued in this algebra A. And this sesquilinear form behaves a lot like an inner product. So it satisfies the kind of things you want an inner product to satisfy. For example, psi1, psi2 star is psi2, psi1. Psi with psi is a positive element of the C-star algebra A. And there's some other conditions. We don't have time to go into the details. So it's like a Hilbert space, but the overlaps are valued in a possibly non-commutative algebra. So that leads to the idea of quantum mechanics with non-commutative amplitudes. The basic idea is to replace the Hilbert space by a Hilbert module, so H is replaced by E. So if I have psi1 and psi2 in E, their overlap is valued in this non-commutative algebra A, this possibly non-commutative algebra A. And therefore, the Born rule is not obvious. You see, in quantum mechanics, when we talk about the probability of measuring an eigenvalue lambda, we write expressions like this, psi lambda psi star. And that's a real number between 0 and 1. In QMNA, quantum mechanics with non-commutative amplitudes, if we mindlessly copy the formulas from the textbooks, well, we'll get an expression like this, which is valued in some possibly non-commutative algebra A. So we'll deal with this question, but first let's look at our two examples of C-star algebras and what are the Hilbert modules that go with them. So in example 1, we have the Hilbert bundle over a commutative manifold, and the module is just the sections of H over X, and the algebra is just the continuous functions on X. And here's the picture from before, and now we have to decide what is the inner product of two sections. It's got to be valued in this algebra. This algebra is just the continuous functions on X, so this has to be a function on X, and it's the function whose value at little x is just the inner product of these two vectors, psi1 of x and psi2 of x. Simple enough. For example 2, we'll talk about a Hilbert bundle over a fuzzy point. By a fuzzy point, I mean that non-commutative space whose algebra of functions is just A by A matrices over the complex numbers. Little a here is a positive integer. So a Hilbert module then is just the space of B by A matrices. So A acts on the right here. And the sesquilinear form, well, if I have two B by A matrices, I can take psi1 dagger psi2, and that's an A by A matrix. And it satisfies all the axioms we want it to satisfy. So now, what are the observables in QMNA? Well, we should consider the adjointable operators. That is, the linear operators, T, from E to E, so that there exists, not 5, 11. You miscounted. I'm sure. I have it here. Now, what are the observables in... I started late. You're right, it's 12:30, but I started late. What are the observables in QMNA? They're the linear operators, T, from E to E, such that there exists a T star that satisfies this equation. And it turns out that the adjointable operators B are another C star algebra. So will define the QMNA observables to be self-adjoint elements of B. Okay, now that immediately raises a technical problem for the Born rule because there's no spectral theorem for a general C-star algebra, and we'll deal with that. Now, finding a good definition of QMNA states turned out to be a lot harder. It's a lot like trying to open a tin of pineapple without having a proper can opener. It's good to start with another off-the-shelf mathematical definition, which is a C-star algebra state. So a C-star algebra state is a positive linear functional from the algebra to C, which takes the unit to 1. And in our two examples, well, if A is the continuous functions on X and omega is the state, then the value of omega on a function is always the integral of f over x times a positive measure on x. And if A is an A by A matrices and omega is his state, then the general state on T is just the trace of rho times T, where rho is a density matrix. So after wandering in a dark wood for a long time, I finally decided that a good definition of a QMNA state is a completely positive unital map phi from B to A. Now, I don't have time to explain what completely positive means. I'll just say that it's a natural condition that comes up both in math and in quantum information theory. And at this point, you can go on and start talking about dynamics. There's a natural generalization of the Schrödinger equation, actually of the Lindblad equation. But as the Schilling shocker says, we anticipate, before we talk about dynamics, we should finish our discussion of kinematics, namely, what is the Born rule? And the main insight here is that we should regard the Born rule as a map from states times observables times C-star algebra states on this base algebra A to probability measures. And it turns out that for general A, this extra datum of a state on A, together with the complete positivity of phi, give just the right information to state Born rule. So roughly speaking, the formula looks like this. It's you take the projection valued measure of M, you apply the completely positive operator that lands you in A, and then you apply the C-star algebra state omega. But this formula is technically wrong. In order to make the formula technically right, you need complete positivity of phi. I'm not going to explain those technical details, but I'll just tell you what happens for a family of quantum systems over a fuzzy point. So remember, in a fuzzy point, our Hilbert module is B by A matrices. So let's write that as CB tensor CA, or better, HBob tensor H Alice. And let's interpret A as the linear transformations on H Alice. And then you can work out what B is. And it's just the linear transformations on HBob, those B by B matrices acting on the left. And then the Born rule reduces to this expression here, where what I've done here is I've taken a measure, omega, on the state space of A. That's equivalent to a density matrix by the theorem I quoted before. And so we have the trace over HA of rho A. Here's our completely positive map applied to the projection valued measure. Now, the general completely positive map looks like this so-called Krauss form, where if it's unital, then it has the Krauss operators E alpha have to satisfy the sum rule. So here's that formula again. Now we write out the Krauss form. We use cyclicity of the trace, and we recognize that this is what's called a quantum channel applied to rho A. So this last expression is the measurement by Bob of the observable T in the state E of rho A, where Alice prepared rho A and sent it to Bob through a quantum channel E. And the point of this slide, indeed the point of chapter 3, is that you can take at least some statements in quantum information theory and rewrite them in terms of non-commutative geometry. Now, this is a novel statement. Whether it is a useful or an interesting statement, I'm not in a position to say. I merely offer it. So there you have it. 3 points in a talk, to say nothing of the prologue. It's time to wrap up. Now it really is 5 minutes. And, my best paper with Nati had lots of hexagon and pentagon relations. And we spent a lot of time worrying about whether some relations were independent of the other relations. Well, Nati, I've discovered a new independent hexagon relation. There it is. Now, I was quite intrigued that hexagons were also the theme of the poster for this conference. But if you look closely, this poster has a serious mistake. If you look here, you see that's the fusing matrix, not the braiding matrix. It's the braiding matrix that satisfies the hexagon relation. The fusing matrix satisfies a pentagon relation. This poster is wrong. There should have been 12 pentagons, not 10 hexagons. But you know, Nati has enough great results that you could just as easily have filled up 12 pentagons as you could 10 hexagons. So no matter how you factor 60, it's been a spectacular career. And so Nati, congratulations and happy birthday. Yes?
So just to clarify, the last chapter, was this the modification of quantum mechanics, or is this rewriting of quantum mechanics?
Yeah, this is a great question, and I'm still struggling with it. So in, you know, when you work with quantum systems, open quantum systems, and you talk about these things like this Krauss operators and the Lindblad equation and so on, there's a maneuver called going to the church of the larger Hilbert space. It uses something called the Stein-Spring theorem. And so what you do is you take this quantum channel, and using that, you make this bigger church, this bigger Hilbert space. And the point is that the bigger Hilbert space just depends on the quantum channel. It doesn't depend on the state. Okay? So the church and the state are independent. You could take, in what I've explained, this completely positive map and construct a church, but then the church and the state would be dependent on each other, and we know that's a bad idea.
So what's the answer to my question?
The answer is, I'm not sure, but I think it's different, but I'm worrying about exactly this point, about the church of the larger Hilbert space.
But if it's different, there must be a parameter that tells you by how much you kind of the amount of non-commutativity that you can turn off.
Yeah, great question. So, so I'm thinking about various examples of this algebra A. And a good example of this algebra A would be to you'd like to do deformation quantization of a Poisson manifold, but then you don't really get an actual algebra of operators. But you could take a Kähler manifold. And so you could take a compact Kähler manifold and introduce such a parameter, and then try and take a limit. And that's something that's work in progress. I'm trying to work out this formalism in the case where A is the algebra of functions and Kähler quantization of a compact manifold, so I could take the limit as it goes to 0. I did work out the example of the noncommutative torus, and it looks, you know, if the phase is irrational, it looks like something strange.
Okay, time for one more short question. If not, let's thank Greg again.